topic, we're going to be looking at the solution of linear algebra problems. So in the solution of linear algebra problems, we have a number of questions. First of all, what constitutes a solution? How do we find a solution? What if we have too many solutions? What is a normal equation? What is a solution map? What is the geometry of the solution? And what is the pseudo-inverse? These are topics that will be discussed in this set of videos. So our basic equation is this: ax is equal to b. That's the basic equation. And here in general x, so we're looking now, we've kind of backed away from the general concept of linear vector spaces. Now we're looking specifically at linear algebra problems, and in this case actually real linear algebra problems. It could be complex, but we're looking at them in the real form. And A is m by n, B is of dimension m, x is of dimension n. So x is the input space, B is in the output space. Okay, so when you have an equation like this, there are three possibilities for solutions. One is that you can have no solutions or no exact solutions. You can have a unique exact solution, and you could have an infinite number of exact solutions. All right, so the basic problem again could be written down this way. We want to minimize the norm of ax minus b. We want to find x that minimizes this norm quantity where x is in the input space. So this is another way of writing that. Now this minimization problem involves the use of optimization theory. So we're actually going to be, we've actually seen some of that already, constrained optimization problems, when we looked at the projection theorem. The projection theorem was basically the solution to a minimization problem. We're going to actually use the projection theorem here. But there are other minimization problems depending on the kind of problem you're working with. So again, your basic equation, ax equals b, there's three possibilities. Here are some examples of those. So for example, if a is 0 and b is 1. So if a is 0, we can't divide by 0, and so we have no exact solution. Basically, that corresponds to the equations being consistent. That's equal to saying 0 is equal to 1. That's not consistent. Okay. Turns out we can still get a solution to that problem. Only one exact solution is another one. So if a is the constant value, non-zero, and b is a constant value, then I can just divide b by a and get the solution x. Or I could have an infinite number of exact solutions. A is a row, which means x has two elements, and b, so this is like one equation and two unknowns, in which case you get an infinite number of exact solutions. So these are the kinds of things we're looking at. Again, no solution, exact solutions, inexact solutions. So we'll talk about that in terms of least squares. Unique solutions, parameterized solutions. So these are some examples of solutions. The existence of an exact solution. Under what condition does an exact solution exist? Okay, there is a condition. Note that since we have the operator, ax, then b must be in the range of a, right? Because you have the input space, and a maps from the input space to the output space. So if there's an exact solution, b must be in that range. Must be in the range, because there must be an x that gets you there to b. So b must be in the range of a. So for an exact solution, x is a vector that gets to b through a. Any exact solution multiplying by a gives you b. Now, if b is not in the range of a, then no exact solution exists. We saw that last time when we looked at the curve fitting problem. Because of the fact that the data did not go all through the curve fit did not go through all the points, that's a recognition of the fact that this kind of a condition was going on. But that didn't mean we couldn't get useful results out of that linear algebra problem. It just means that b was not in the range of a, and we had to do some work to get that. So this is the concept of an exact solution, and this is the condition. B must be in the range of a. If b is not in the range of a, you will not get an exact solution. If b is in the range of a, you will get at least one exact solution. You may get an infinite number, but you get at least one. Solution map. So we have a contrast between what's called a point solution and a solution map. A solution map is in contrast with a point solution. A point solution is a specific solution x for a specific value b. A solution map is a formula or operator for obtaining a solution. That is, if I give it a new b, the solution map will give me the new a. Okay, so instead of just finding a solution for a problem, the solution map is actually finding me the solution for any input. So as an example, suppose that b is our solution map. So x then is equal to b times little b. Okay, so if I'm given a new b, I have a new x. So this maps a vector b into a solution x. So ax is equal to a little b, a big B times little b. And if this is in fact a solution map, then AB is equal to b. AB times little b is just equal to b, little b. That is, ax is equal to b. So this would be an example of a solution map. In general, there may be multiple solution maps for a given problem. So I'm talking now about some important concepts associated with the linear algebra problem. Lastly, we have what's called the normal equation. The normal equation is actually a condition that comes out of an optimization problem. In optimization, whenever there's a directional derivative of a function and it's equal to 0 at some point, we have what's called a local minimum or a local maximum. Such a point occurs when the gradient is orthogonal to the error. Okay, so there's that orthogonality condition. And such a point is a first-order necessary condition for optimality. In the case of our linear algebra equations, it means that the residual, the error, must be normal to every vector in the span of A. So we kind of saw that already when we looked at the projection theorem. And that's basically, the projection theorem actually leads to a normal equation. We'll see that here in a little bit. But so these are some important topics to consider when looking at the solution to the basic linear algebra problem. We're going to move on to the overdetermined problem.